Well, to simplify these two ratios, the first thing we need to do is resolve the units. After all, ratios have no units. So on number 5, let's start with this. I'm going to express them both as milliliters. And then it's pretty straightforward. See, I can divide, just like I can divide out the factors of 10, I can divide out the milliliters, just like you did in your chemistry class with your dimensional analysis. And therefore, my ratio is 600 to 1, expressed as a fraction, 600 over 1, or with a colon. It's all good there. So, number 6, you got the idea by now. So let's just do this. Change in terms of feet. And easily we can divide out the tens. Now we have an extra factor of 2 in there. And we can divide that out, no problem. And we're going to see 264 to 1. And that would be our ratio. Okay, 2 more straightforward ratios. Over here is 7 foot to 12 inches. Now, I don't even have to do that. You know, there's 12 inches in a foot. You might just see that as 7 to 1 right away. But maybe you want to be more formal. Just like we did before, we're pointing this out. I could show this as a product of this conversion factor, this 12 inches to 1 foot. Because when I do all this dividing, look at this. The units, the feet divide out. The inches divide out. And the 12s divide out. Oh, that's very convenient. And that leaves us with a ratio of 7 to 1. Over here, in the metric side, not so much different. We know that that every meter is 100 centimeters, so 2 meters, 200 centimeters. Gosh, I wish we had that system. So, centimeters there, divide out the tens. Now, 8 and 20 still have some common factors. Can we do that really fast? Sure, that's 2 to 5, or 2/5. Well, let's make sure we got our ratios down. I'm looking at this width to this length, 5 inches to 15 inches. Or, another way of saying that, 1 to 3. Simplified it on you. Easy. Well, number 12. See, that would be 16 to 18. 16 centimeters to 8 centimeters. And that simplifies to the ratio of 8 to 9. Still easy. Well, number 13. Now this is drawn to scale. This is 320 to 10. But it's 320 centimeters to 10 meters. If we're going to do this right, we need to have the same units. Because after all, ratios are unitless. The only way we're going to get there is by starting out with the same units. 320 centimeters to 1,000 centimeters simplifies to the unitless ratio of 8 to 25. Well, let's get to work with this ratio. I'm first going to draw a picture. And I've got a rectangle here with a ratio of 10 to 1 for its length to its width. So, reminding myself that the perimeter, I add up all the sides. So remember, I've got the 10x twice, and I've got those 1x's twice. Or I could just say 22x. 22x is equal to the perimeter of 154. Solving for x is 7. Substitute back, and we're done. Wow, this takes me back to the first chapter, segment addition. I've got the blue segment and the red segment, that is AB and BC, all add up to or combine to AC. This 36 right here. Now, the only thing different from this in chapter 1 is that we now have a ratio. Now, I said, well, let me see, that blue, that's going to be 2 parts to the red, 7 parts. Now, if I want to make the picture look realistic, I suppose it might look more like that. That's about right. 2x is to 7x as AB is to BC. And the whole thing together, AC is 36. So you can see how this is going to work. The blue, 2x, plus the red, 7x, equals 36. Segment addition. Easy. And there you go. Now, I won't bore you with arithmetic, but the variable x is certainly 4. What do you do then? Substitute. And there you go. So in this example, it must be 8 and 28. That'll give me my 36. The angles in a triangle are in this extended ratio. So let's find out what they are. We know these three angles must add up to 180, theorem 4.1, also known as the triangle sum theorem. We can, we can simplify that and solve it. Add up all those x's, and x is 10. Now my substitution. So I've got 3 10s, 5 10s, and 10 10s. 30, 50, and 100, that adds up to 180. That checks out okay. My triangle looks a lot like this. Well, here we go. We've got a couple supplementary angles. Now, they don't have to be a linear pair, but it's easy to draw this picture. And the ratio is 5x to 3x. I don't know where this goes, but all I know is, well, okay, 5x is bigger than 3x. So I'm going to imagine the picture looks like this. And I know this red angle and this blue angle are going to combine to 180 degrees. How easy is that? Combine some terms, and I divide. I now have a value for x, and let's just substitute. There you go. 112 and a half, 67 and a half. Easy. Well, here we go. We've got a diagram here of an exterior angle, angle 1, and its adjacent interior angle, angle 2. Well, of course, these two angles are supplementary. I've got no idea anything about them until I introduce this concept, the ratio. Let me see if the adjacent interior angle, the exterior angle, that's the red angle, to the blue angle has a ratio of 1 to 4. Now, I could actually just visualize the answer, but let's go through this mathematically. I'm going to say then that angle 1 is x degrees. Well, then I guess angle 2 is 4x. So I could just say angle 2 is 4 times as big as 1 and I'm done. But let's be a little more thorough. I'm going to add those two together, get 180. So I can solve for x. X must be 36 degrees. So I don't have to wonder if it looks like this or this. It actually looks a lot like this, because that would be a 36 degree angle for angle 1. And therefore, the resulting triangle is absolutely obtuse, because angle 2, 144 degrees. Well, I've got a square here. Don't know how big the sides are, but I know they're all the same. I'm going to assign them a value of s. Well, if the side is s, I know the perimeter is 4 times s. So if I want to know the ratio of the perimeter to the side, or to a given side, well, it's 4s, or 4 s's, to 1s. And if I would divide out those s's on both sides of this ratio, 4 to 1. Well, let's apply this ratio to this figure. AB is to BC as 3 is to 8. Well, that's the ratio, so well, let's set it up. I can write it out this way. P is to 24 as 3 is to 8. Now, you all know that you can do the cross product. Yeah, we could do that. But this one is a candidate for a much easier operation, because the more ways you can work a proportion, the better off you are. Let's suppose I just use similar fractions. I'm just going to multiply right here. I'm going to multiply the 3/8 by 3/3. And as you can see, what I end up with is 9/24. By using that similar fraction, now P over 24 equals 9 over 24. Well, I can actually just multiply both sides by 24. In other words, if P over 24 is 9 over 24, then quite simply P is 9. So similar fractions might be another way for you to do these quick exercises, and I'm sure we'll hit some where we have to cross multiply. So think about that. Let's do another exercise with these ratios, this time a little more exciting because I've got this variable expression down here. So again, AB is to BC as 3 is to 4. So let's write this down as a ratio. Now I'm going to write it this way first. 3 is to 4 as 60 is to 10 cubed plus 15. Now, this is a case where we're going to use the cross product, because I'm going to multiply the extremes, I'm going to multiply the means. Now remember, when I'm multiplying the 3 by this expression, that's 3 times the first term and 3 times the second term. 4 times 60, well that's a piece of cake. You can do that in your head. I mean, 4 6s are 24, so that's 240. But let's just do it like this. Remember, 3 times 10 cubed is 30q. 3 times 15 is 45. Distribute, distribute, distribute. That's equal to 240. And let's see, where do we go from there? Let's subtract 45 from both sides of the equation. What's next? Divide, divide. There you go. How easy is that? What? I didn't divide, I just repeated it. Who's in charge here? Let's divide now. There you go. Now we're done. So Q, 6.5. Another rectangle exercise. There's our picture. The ratio of the width to the length is 5 to 6. 5x to 6x. Easy. I know the area, so I set up an equation. Remember, when I multiply the 5x and the 6x, because that's how we get the area of a rectangle, base times height, or length times width, that's going to be 30x squares. So now we're going to have to do the division. That works out pretty well. And then, well, if x squared, 144, we'll take the square root of both sides, and really we'll take the principal root, and I see that's going to be 12 inches. Then I can substitute it there. It says, okay, I've got 5 12s and 6 12s. So my dimensions will be 60 and 72 inches, respectively. Well, tiling. Oh, we love this in math. We've got a room with a perimeter of 60 feet, and we're assuming this is a rectangle. I hate assuming. We've got this ratio here of 6 to 3. I would have said 2 to 1. And we're going to put down 12-inch square tiles. First thing I'm going to do is assign some variables, because I recall that the perimeter of a rectangle is 2 times the quantity length plus width. Well, I'm going to let the width equal x. The length then is 2x, twice as big, and the perimeter is 60. When I substitute into this fine equation, this is the relationship I get. Easy enough. Now let's just put in the proper variables. I'll replace length with 2x and width with x. Now I've got something I can solve. And let's see, I chose to, instead of distributing, I divided both sides by the 2. And now I've got 2x and 1x. I can combine those terms. And 3x's are 30. Each x is 10. Now, if you wanted a picture of this, I'm guessing that's what it would look like. Because again, the perimeter is 60. And in a ratio of 2 to 1, 20, 10, that's a semi-perimeter of 30. Double that, you got 60. So, well, let's see. What was I going to come? Oh yeah, let's move on to moving on to some answers here. Well, clearly 20 times 10, I'm going to end up with is 200 tiles. Oh, look at that. Oh, could you imagine a job that comes out like this, where all the tiles, not a tile breaks, and they fit, you don't have to cut any of them? Wow, I want that project. There you go. 200 tiles, $196. Keep the change.